Bismillah ar-Rahman ar-Rahim. Assalamu alaikum wa rahmatullahi wa barakatuhu. Welcome to the Computer Architecture and Assembly language class. Now we move into the second part of this chapter, which focuses on performance. Performance is the key to understanding the underlying motivation for hardware and its organization. When we study why processors are designed a certain way, performance is usually the driving factor. We measure, report, and summarize performance to enable users to make intelligent choices. Whether you are buying a laptop, building a server, or designing a new chip, you need performance data to compare options and select what looks best. So, this leads us to three important questions. First, why is some hardware better than other for different programs? A processor ideal for video editing may not be best for database work because both have the different program. Second, what factors of system performance are hardware related? We need to identify which components actually impact speed and efficiency. Third, how does the machine's instruction set affect programming and its performance? The instructions a processor can execute directly influence how fast programs run. So these are the questions we will explore in this section. This slide uses an airplane analogy to show that performance depends on how you measure it. Look at this table comparing different airplanes. We have passengers and its range and speed in miles per hour. How much faster is the Concorde compared to the 747? The Concorde flies at 1350 miles per hour, while 747 it flies at 610 miles per hour. So the Concorde is of course more than twice as fast. Second is how much bigger is the Boeing 747 than the Douglas DC-8. The 747 carries 470 passengers, while the DC-8 carries 146. So the 747 carries more than three times as many people. So which of these airplanes has the best performance? Now the answer depends on what you care about. If you want speed, the Concorde is best. If you want passenger capacity, the 747 is best. If you want range, the DC-8 flies farthest. So performance is not a single number. It depends on how your perspective and what you are trying to achieve. So the sample applies to the computer as well. In the computer also we need to see that what factor we need to observe while checking its performance. When we talk about computer performance, we need to be clear about what we are measuring. There are two main ways to look at performance. First is the response time, also called elapsed time or latency. This measures how long it takes for a job to run from start to finish. For example, how long do I wait for a database query to complete? How long does it takes to render a video? This is about the user's experience of waiting. Okay. Second is throughput. This measures how many jobs the machine can run at once, or the average execution rate. It answers the questions how much work is getting done over a period of time. This is about the system's overall productivity. Now, here are two questions to think about. If we upgrade a machine with a new processor, what do we increase? A faster processor typically reduces response time for individual tasks. So if we add a new machine to the lab, what do we increase? Adding another computer increases throughput because more jobs can run simultaneously across multiple machines. So response time is about speed for one task, while throughput is about total work completed. Both are valid measures of performance depending on what you care about. Now let's look more closely at execution time and what it actually includes. First, we have elapsed time. This counts everything from the moment your program starts to the moment it finishes. It includes disk and memory accesses, waiting for input and output, and even time spent running other programs in the background. So elapsed time equals CPU time plus wait time. Next, we have CPU time. This is the time the CPU spends actually working on your program. It does not count waiting for input and output or time spent running other programs. CPU time can be divided into two parts: user CPU time and system CPU time. User CPU time is the time spent executing the lines of code that are in our program, while the system CPU time is the time spent in operating system calls made on behalf of our program. So CPU times equals user CPU time plus system CPU time. So this means elapsed time equal user CPU time plus the system CPU time plus the wait time. When we talk about performance in this course, we are usually interested in the CPU time, also called CPU execution time or simply execution time. This is the time actually spent running our programs instructions. Now we need a way to compare performance between different machines. Performance is designed as the reciprocal of execution time. So performance of machine X equals 1 divided by the execution time on machine X. This makes sense because a machine that finishes a program faster has high performance. If execution time is smaller, performance is larger. If the execution time is larger, then the performance is smaller. When we say machine X is n times faster than machine Y, we mean that the ratio of their performance equals n. So performance of X divided by performance of Y equals n. For example, if machine X executes a program in 2 seconds and machine Y executes the same program in 6 seconds, then performance of X is 1 by 2 based on this formula, and the performance of Y is 1 by 6. So the ratio is 1 by 2 divided by 1 by 6, which equals to 3. So machine X is 3 times faster than machine Y. So this gives us clear and consistent way to compare the computer performance. Okay, instead of reporting execution time only in seconds, we need to understand how the processor measure time internally. In modern computers, hardware events progress cycle by cycle. Each operation, like multiplication or addition, takes a sequence of these cycles to complete. So the machine cycle is the fundamental unit of time inside the processor. Execution time in seconds can be calculated as the number of cycles per program multiplied by the number of seconds per cycle. Execution time in seconds can be calculated as the number of cycles per program multiplied by number of seconds per cycle. So clock ticks indicates the start and end of each cycle. The cycle time is the time between ticks, measured in second per cycle. So the clock rate, also called frequency, is the number of cycles per second. 1 hertz equals 1 cycle per second. 1 megahertz equals 1 million cycle per second, and 1 gigahertz equals 1 billion cycles per second. I hope that you observed whenever you are buying a laptop or even a smartphone, the the CPU is in the hertz. Okay, it is execution performance shows in the hertz. That, for example, its CPU is 2 gigahertz. It means that it can process 2 billion cycles per second. So that is the number which shows the performance of that CPU in the laptops or your smartphones. Okay, here is an example. A 200 megahertz clock has a cycle time of 1 divided by 200 million, which equals 5 nanoseconds. So 5 nanoseconds is 5 billionth of a second. I hope you are familiar that how we calculate like this nanoseconds, if it's like it's milli, micro, and then nano. I hope you are familiar with that. So when we see a processor advertised as 3.5 gigahertz, that means it can execute 3.5 billion cycles per second. Each cycle is incredibly fast, lasting only a fraction of a nanosecond. Now you can imagine the speed of the execution inside the CPU. Okay, so this slide presents the fundamental performance equation that ties everything together. CPU execution time for a program equals the number of clock cycles for that program multiplied by the clock cycle time. Another way to write this is the seconds per program. Okay, another way that it can write is that it is second per program equals cycles per program times second per cycle. This equation is important because it shows exactly what factors determine how fast a program runs. So the number of clock cycles for a program depends on the instruction counts and how many cycles each instruction takes. The clock cycle time depends on the processor's hardware design and the manufacturing technology. Suppose a program runs on a processor with a 2 gigahertz clock rate. So 2 gigahertz means 2 billion cycles per second. So cycle time is 1 divided by 2 billion, which equals 0.5 nanoseconds. Assume this program requires 10 billion clock cycle to execute. So the execution time equals cycles per program times cycle times. So 10 billion cycle times 0.5 nanosecond equals 5 seconds. So this is how we calculate the execution time of a program. In simple terms, the example which I have just quoted, 0.5 nanosecond means each cycle take half a billionth of a second. If you have 10 billion cycles, so each taking half a billion of a second, the total time is 10 billion into 0.5 billions. It means 5 seconds. So to improve the performance, we have three options. Okay, so what are these options? Option one is reduce cycle per program. If we optimize the program or improve the architecture so it only needs 10 billion cycles, means instead of 10 billion cycles, it needs only 8 billion cycles, execution time becomes 8 billion times 0.5 nanoseconds, which equals to 4 seconds. So performance improves by reducing the number of cycles. Okay, so earlier, in the earlier example, it was taking 5 seconds, or now with the reduced cycles per program, it takes the 4 seconds. So we can save 1 second with this technique. Option 2 is reduce cycle time. If we keep the program at 10 billion cycles but manufacture a fast processor with 2.5 gigahertz. So now instead of 2 gigahertz, we use 2.5 gigahertz clock rate. Cycle time becomes 1 divided by 2.5 billion, which equals to 0.4 nanoseconds. So again, execution time becomes 10 billion times 0.4 nanoseconds, which equals to 4 seconds. So performance improves by making each cycle shorter. So the third is increase clock rate. This is equivalent to option 2. So increasing clock rate from 2 gigahertz to 2.5 gigahertz means the same reduction in cycle time. So execution time becomes 4 seconds. So all these options achieved the same 4-second results but through different methods. So in reality, designs often combine these approaches for maximum performance gain. Now we need to understand that what determines the number of cycle a program takes. One simple assumption might be that the number of cycles equals the number of instructions. So if a program has 6 instructions, it would take 6 cycles. The diagram shows this idea with each instruction taking exactly 1 cycle. However, this assumption is wrong. So different instructions take different amounts of time measured in cycles. Some instructions complete in 1 cycle while other needs multiple cycles. Why is this? There are several reasons. So let's look at why different instructions take different number of cycles. First, multiplication takes more time than addition. The hardware required to multiply number is more complex and needs more cycles to complete. I hope in the computer organization you might learn about the Booth's algorithm, which multiplied the two numbers, and you have seen that there are a lot of steps and execution. So multiplication isn't that simple. So it takes the more cycles. Second is floating point operations that take longer than the integer ones. So calculations with decimal numbers are more complex than the whole number operations. Third is accessing memory. It takes more time than accessing a register. Registers are inside the CPU and extremely fast. Memory is outside the CPU and significantly slower. So instructions that load or store data from memory require extra cycles to wait for the data to arrive. So here is an important point to remember. Changing the cycle time often changes the number of cycles required for various instructions. This is because cycle time is tied to the hardware design. If you make the clock faster, some instructions that previously completed in one cycle might now need 2 cycles because the hardware cannot finish the operation in that shorter time. So there is a trade-off between cycle time and cycle per instruction as well. Let's walk through a practical example that applies everything we have learned. We have a computer A with a 400 megahertz clock and it runs a program in 10 seconds. We want to help a designer build a new machine B that will run the same program in 6 seconds. So we need to improve the performance by 4 seconds. The designer plans to use new technology to substantially increase the clock rate. However, this increase will affect the rest of the CPU design. Because of these changes, machine B will require 1.2 times as many clock cycles as machine A for the same program. So machine B needs more cycle to execute the program, but each cycle happens faster. So the question is, what clock rate should we tell the designer to target? We need to find the clock rate for the machine B that achieves the 6 second execution time, given that it takes 1.2 times more execution than machine A. So this slide indicates the key terms we use when discussing performance. A given program will require 3 things. It will require some number of machine instructions, it will require some number of clock cycles, and it will require some number of seconds to complete. We have a vocabulary that relate these quantities. Cycle time is seconds per cycle. So this tells us how long each individual cycle takes. Clock rate is cycles per second. This tells us how many cycles happened in 1 second. So clock rate is the reciprocal of cycle time. So average CPI stands for cycles per instructions. This tells us on average how many cycles each instruction takes to execute. So different type of programs have different average CPI. For example, a floating point intensive application might have a higher average CPI because floating point operation takes more cycles than simple integer operations. MIPS stands for millions of instructions per second. So this measures how many million instructions the processor can execute in 1 second. So MIPS would be higher for a program using simple instructions that complete quickly. However, MIPS can be misleading because different instructions do different amount of work. So a program with high MIPS is not necessarily faster if each instruction does very little. So performance is ultimately determined by execution time. That is the bottom line. A computer is faster if it completes a program in less time, regardless of what happens internally. Now, looking at three variables, do any of them alone represent equal performance? Number of cycles to execute a program? Not necessarily. A program might take many cycles, but if each cycle is very short, execution time could be still be slow. Then the number of instructions into a program, also not enough. A program with fewer instructions might still take longer if those instructions are complex and require many cycles each. Then number of cycles per second, which is clock rate. A higher clock rate is good, but if instructions take more cycles on that processor, then performance might not improve. Next is average number of cycle per instructions, or the CPI. So a low CPI is good, but if the program has many instructions or the clock is slow, execution time still could be high. So average number of instructions per second, or MIPS. High MIPS sounds good, but if each instruction does very little work, the program might still run slowly. So none of these variables alone tells the whole story. Only execution time directly measures performance. The other factors interact in complex ways, which is why we need the full performance equation to understand what is really happening. So this slide brings everything together into the complete performance equation. So CPU execution time for a program equals instruction counts for that program multiplied by average CPI multiplied by clock cycle time. So let's break down each component. Instruction count is the total number of machine instructions executed by the program. This depends on the program itself, the compiler, and the instruction set architecture. Average CPI is the average number of clock cycles per instruction. This depends on the processor hardware and the mix of instruction types in the program. Different instruction takes different number of cycles, which we discussed in the earlier slides. And the next is the clock cycle time. This depends on the processor's hardware design and manufacturing technology. So multiplying these three give us total execution time. So this equation is powerful because it shows exactly where performance improvements can come from. So we can reduce instruction count through better compilers or richer instructions. We can reduce average CPI through more efficient processor designs, and we can reduce cycle time through faster hardware technology. The challenge is that these factors often interact. Changing one can affect the other, which is that makes computer architecture both complex and interesting as well. Let's work through a simple example using the performance equation. We have a processor running at a 20 gigahertz clock rate. That is 20 times 10 to the power of 9 cycles per second. So first we need clock cycle time. Cycle time is the reciprocal of clock rate. So cycle time equals 1 divided by 20 times 10 to the power of 9 second. The program has 200 instructions and we assume each instruction takes one clock cycle. So the instruction count is 200 and CPI is 1. So execution time equals 200 times 1 times 1 over 20 times 10 to the power of 9. 200 divided by 20 times 10 to the power of 9 equals 10 times 10 to the power of negative 9 seconds. So if we execute it, so so this program takes 10 nanoseconds to execute on this processor. This example shows how the performance equation work with the simple numbers. In real programs, CPI is rarely exactly 1 because different instructions take different number of cycles, but the calculation method remains the same as per this equation. Now, we need to understand what factors actually influence the average CPI or the cycles per instructions for a program. So the first major factor is the performance of the pipeline. Pipelining is a technique used by all modern processors to execute instructions. So instead of waiting for one instruction to finish completely before starting the next, the processor overlaps instructions executions. While one instruction is being executed, the next is being decoded and the one that is being fetched. However, pipeline stalls and hazards can occur when an instruction depends on the result of a previous one that is not yet complete. These stalls increased CPI because instructions take extra cycle to wait for dependencies to be solved. So the second major factor of the performance is the memory system. When an instruction needs to load data from memory, it may have to wait if that data is not already in cache. So this is called a cache miss. Memory access time are much slower than the processor speed. So waiting for data from main memory adds significant cycles to instruction execution. The more cache misses a program has, the higher its average CPI will be. So even if a processor has a fast clock and efficient pipeline, poor memory performance can drastically increase CPI and slow down the execution. This is why memory hierarchy design is so important in the modern computer architecture. Let's summarize what we have learned about performance. First, performance is specific to a particular program. A processor may run one program very quickly and another program slowly. So when we talk about performance, we must always specify which program we are measuring. Total execution time is the most consistent and reliable summary of the performance because it directly measures how long the program takes to run. For a given architecture, performance increases can come from three main sources. Okay, increase in clock rate as long as they do not adversely affect the CPI, improvement in processor organization that lower the average CPI, and compiler enhancements that lower CPI or reduce the instruction count. Here is an important pitfall to avoid. Do not expect improvement in one aspect of a machine's performance to automatically improve total performance. For example, increasing clock rate might require more pipeline stages, which could increase CPI and cancel out the benefit. Or improving CPI might require more complex hardware that slows down the clock. All factors are interconnected. And remember, execution time is the best measure. It captures the combined effect of instruction count, CPI, and the clock rate. So if execution time goes down, performance has improved regardless of what happened to the individual factors. So these all are relevant to the performance of the computer system. Thank you so much. Assalamu alaikum wa rahmatullahi wa barakatuh.